What specific problem does your proposed method aim to solve in video generation, particularly regarding motion representation and control?
Our proposed method addresses the challenge of effectively representing and controlling motion in video generation, which is often inadequately conveyed through text prompts alone. We identify that text struggles to capture the nuances of motion, such as speed, trajectory, and timing, leading to ambiguity in video generation. To solve this, we introduce a motion representation using spatio-temporally sparse or dense motion trajectories, which allows for a more expressive encoding of motion. Additionally, we propose motion prompt expansion, enabling users to translate high-level requests into detailed motion trajectories, thus bridging the gap between user intentions and the motion representation. This approach enhances the granularity of motion control, facilitating tasks like object manipulation, camera movement, and motion transfer, ultimately leading to more realistic and engaging video outputs.
Can you explain how your method functions in detail? Please illustrate the steps involved in training the control net with motion prompts and how they are integrated into the video diffusion model.
Our method functions by integrating motion prompts into a pre-trained video diffusion model, specifically Lumiere, through a control net architecture. The training process begins with preparing a data set of videos paired with point trajectories, which are extracted using the bootstrap tracking method. Each video is represented by a set of point trajectories, denoted as P in math BBR n times T times 2, where n is the number of tracks and T is the length of each track. During training, we construct a conditioning signal, C in math BBR T times H times W times C, by associating each track with a unique embedding vector and placing these embeddings at the corresponding spatial temporal locations, while ensuring visibility flags are applied to manage occlusions. The control net is then trained using standard diffusion loss, optimizing the model to generate videos conditioned on both the text prompt and the motion prompts, allowing for fine-grained control over the generated motion. This approach enables the model to generalize effectively across various motion types, as it learns from a diverse set of trajectories without being explicitly trained on specific motion patterns.
Could you provide a simple example to illustrate the mechanics of motion prompt expansion? How does this example help clarify the overall functionality of your approach?
A simple example of motion prompt expansion is converting user mouse drags into semi-dense motion trajectories, allowing users to manipulate elements in an image, such as hair or sand. When a user drags their mouse across a still image, the system translates these movements into point tracks that represent the desired motion. This process enables users to interact with the image dynamically, effectively bridging the gap between high-level user intentions and the detailed motion representation required for video generation. By facilitating this interaction, our approach demonstrates how motion prompts can enhance user control and engagement, ultimately leading to more expressive and realistic video outputs. This example illustrates the core functionality of our method, showcasing its ability to translate simple user inputs into complex motion trajectories that guide the video generation process.
What are the advantages of using your motion trajectory representation compared to traditional optical flow or other motion representations in the context of video generation?
The advantages of using our motion trajectory representation over traditional optical flow and other motion representations in video generation are significant. Firstly, our point trajectories can handle occlusions effectively, which is a critical limitation of optical flow that often fails to account for objects disappearing from view. Additionally, point trajectories allow for both sparse and dense tracking over arbitrary temporal durations, providing greater flexibility in motion representation. Unlike optical flow, which can accumulate errors over time, our approach maintains robustness and accuracy in motion tracking. Furthermore, our model's ability to generalize across various motion types without requiring specific training on those motions enhances its versatility, making it suitable for a wider range of video generation tasks.
How did you validate the effectiveness of your model? Please detail the experimental design, datasets used, and metrics employed to compare against baseline methods.
To validate the effectiveness of our model, we conducted a quantitative evaluation using the validation split of the Davis video dataset, where we extracted first frames and tracks to feed into our model, along with automatically generated text prompts. We varied the number of conditioning tracks from a single track to 2048 tracks to assess performance across different densities. Our model was compared against two recent works, Image Conductor and Drag Anything, using metrics such as PSNR, SSIM, LPIPS, and FVD to evaluate the appearance of the generated videos, and endpoint error EPE to measure how well the generated motion matched the conditioning tracks. Additionally, we performed a human study involving a two-alternative forced choice test with 180 questions, assessing which videos better followed motion conditioning, exhibited more realistic motion, and had higher visual quality. The results indicated that our model outperformed the baselines in almost all cases, demonstrating its effectiveness in generating videos that align with user-defined motion prompts.
What specific quantitative results did you obtain from your experiments, and how do these results demonstrate the performance of your model relative to the existing baselines?
In our experiments, we evaluated our model against two recent works, Image Conductor and Drag Anything, using metrics such as PSNR, SSIM, LPIPS, and FVD to assess the appearance of generated videos, and endpoint error EPE to measure how well the generated motion matched the conditioning tracks. The results indicated that our model outperformed the baselines in almost all cases, particularly in terms of visual quality metrics. Although Drag Anything showed better EPE with fewer tracks due to its effective latent warping module, it suffered from visual artifacts, resulting in lower PSNR, SSIM, LPIPS, and FVD scores. Additionally, in a human study, our approach was preferred over the baselines across all categories, including motion adherence, realism, and visual quality. These findings collectively demonstrate that our model not only achieves superior performance in quantitative metrics, but also resonates better with human evaluators compared to existing methods.